Hey everyone, welcome back, and today let's solve Leetcode problem 3243 titled Shortest Distance After Road Addition Queries 1. So we're given an integer n and a 2D integer array queries. There are n cities labeled or numbered from 0 to n minus 1. Initially, there is an undirectional road from city I to city I plus 1 for all I that are in bounds or less than n minus 1 and greater than or equal to 0. So queries at index I that has a length of 2, u sub I and v sub I represents the addition of a new undirectional road from city u to city v at that index I. And after each query, we need to find the length of the shortest path from city 0 to city n minus 1. That's already hinting a good algorithm that we can use to solve this problem. We need to return an array answer where for each I in the range of 0 of the length of our queries minus 1, answer at index I is the length of the shortest path from city 0 to city n minus 1 after processing the first I plus 1 queries. So in example 1, they also give us an image to better visualize this. We have n to be equal to 5, and we have queries of 3 different inputs, or a length of 3, and we output a length of 3 output for each query at each index I, right? In this case, we output 3, 2, 1, right? Because in the image it says, the first image says, after the addition of the road from 2 to 4, the length of the shortest path from 0 to 4 would be 3. Okay, and after the addition of the road from 0 to 2, then the length of the shortest path from 0 to 4 is 2. And after the addition from of the road from 0 to 2, the length of the shortest path from 0 to 4 is 2. Okay, and after the addition of the road from 0 to 3, then the length of the shortest path from 0 to 4 is 1. And that's why we'd output 3, 2, 1. So in example 2, we have our input n to be 4 and our queries to be length 2, and so we output a result of length 2 as well. Again, it should be the same length as our queries input array because it will have the same amount of outputs. And in the explanation images, we see that after the addition of the road from node 0 to 3, the length of the shortest path from node 0 to node 3 is 1. Okay, and after the addition of the road from 0 to 2, the length of the shortest path still remains 1. Okay, and for the constraints, we see that n is going to be within 3 and 500 inclusive, and the length of our input array queries is going to be within 1 and 500. The queries at any index I is going to have a sub-length of 2, right, which is good because we don't have to handle any edge cases when it's not 2, and we see that queries at any index I, index 0, is going to be strictly less than queries at that I at 1, which is also going to be less than n and greater than or equal to 0. And queries at index I1 minus queries at index I0 is still going to be greater than 1. And there are no repeated roads among the queries. So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution. And then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so if you guys haven't noticed yet, this is indeed a graph problem, and in my opinion, I think they kind of hint which algorithm that you can potentially use when they actually say that we want to find the length of the shortest path from the two nodes, city 0 to city n minus 1. And that path that we're going to be using to approach this problem is going to be using Jigstow's algorithm, right? It's a well-known shortest path algorithm that we can use for weighted graphs, right? And the way we actually are going to structure our solution is we're going to use priority queues, and in Python it's going to be from the heap queue module, and a graph representation through a dictionary of adjacency lists, right? Which can be used with the default dictionary or the default dictionary or data structure in Python from our collections module. So for a quick high-level rundown of how our algorithm is going to work, we're actually going to have a graph representation, right? We're simply going to represent these cities and their roads using a graph in our hash map where the keys are these city numbers and the values or the key value pairs are lists of tuples, right? And they're going to have length 2, the neighbor and its corresponding weight, which represents the roads. And we're going to use Dijkstra's algorithm to find the shortest path using a priority queue to repeatedly explore the city with the smallest current distance. Okay, and as we do that, we have to update the shortest known distance for all of our neighboring cities, and we're going to do this dynamically. Okay, and for our dynamic updates, we're going to process each query by adding a new road to the graph. And after we actually add each road, we have to rerun or repeat the Dijkstra's algorithm to compute the shortest path between those two nodes. And we'll have a final answer, a result array, which simply is going to, as you probably expected, store the results of the shortest path for each query in an array, or rather an answer list. Okay, so with that out of the way, let's go ahead and dive straight into the code here. So like I was talking about before, we're going to first need two modules to actually import to gain access for better practice, rather, in Leetcode of our two data structures that we need, the heap queue data structure, or rather module, and the default dictionary data structure from the collections module. So I'm going to say import the heap queue, is what it's called in Python. And I'm also going to import my default dictionary data structure from my collections module. And default dict is, again, basically a subclass of our Python's dictionary that actually simplifies our as we actually create our graph, because it initializes values as empty lists as the default automatically. Hence the name default dict. Even if we don't have a key in our hash map that already is defaulted to basically an empty list. Right, it's already a defaulted key, and so we don't have to actually check if it's in our hash map or not. We can already just go ahead and start incrementing or updating its value in the hash map. So from our collections module, we want to import the subclass, I think that's how you spell it, of our default dict. Okay, so now that we've got our modules and our data structures completely imported in our domain for best practice, now let's actually start initializing our graph representation. So I'm going to initialize my graph, and it's going to be initialized to a default dictionary. And for the kind of data structure that I'm going to pass in, okay, I spelled this completely wrong, default dict, okay, and I'm going to have a list as my keys, right? So once I do that, now I want to actually loop through the range of n-1. So for I in the range of n-1, non-inclusive, I want to add to my graph at that index I, so graph at the key I dot append the basically a tuple of length 2, like we talked about before. The first value in this tuple is going to be I plus 1, and it's going to be followed by a simple 1. What does this actually mean? Well, this is representing the road from city I to city I plus 1 with a weight of 1. That's our second parameter. Right? We're simply storing the adjacency list representation of the graph, right? We're, again, in this for loop here, we're initializing our default roads, right? So for each city I from 0 up until n-2, right? Because in for loops, the Python's parameters is n-1 and exclusive, we're going to add a road with I plus 1 with a weight of 1. That's our second parameter in this graph that we're adding. So now let's actually define our Dijkstra's algorithm helper function that we can use to call on the nodes. So def Dijkstra, I still don't know how to spell this. I think it's D-I-J-K-S-T-R-A. Dijkstra's, I think that's how you spell it. It could be wrong. And we don't actually need any parameters for this problem, and you'll see why. And so first, I'm going to have rather initialize a distances list. So I'm going to say distances, and I'll explain this right after. It's going to be equal to the float of infinity, right? I'm sorry, the float of infinity, okay? And this is going to have a dimension, or rather, be multiplied by our input n. And we're also going to have, or rather, initialize distances at index 0 to be kind of initialized to 0 as our base value. And then we want to set PQ to be equal to a list of a tuple of length 2, marking the distance in its corresponding city initialized to 0, 0. So what do all of these three data structures and variables really do? Well, distances is simply going to be a list where distances at every index I is going to represent the shortest distance from city 0 till that index or city or node city I. And we're going to initialize all of these base distances to the float of infinity with the same length as n, except for the starting city, right? It's going to have or rather, it's going to have an initial value of 0 because we want to go from city 0 to other nodes. And so we don't actually have to do anything to go to 0 because we're already at 0. So it's going to have a length of 0. That's kind of our base value that we have to build off of. So we're initializing the distances at the initial or 0th city to be or 0 distance. Right? We don't have to go anywhere. We don't have to travel anywhere. It's simply marked or initialized at its base value of 0. Okay, and PQ is short for priority queue, right? It's going to store the pairs, basically current distance and the current distance to the city to track which city that we have to process next. So now we have to have our standard kind of basically data structure processing of all the different nodes. So while PQ is non-null, so while we still have nodes to process, we want to initialize our current distance and our actual city, right? This is unpacking, right? Because we're popping off an element from our PQ priority queue or heap with a length of 2. And so the current distance is going to be initialized to the current distance, and the city is going to be initialized to our actual city that we're popping off the most recent element from in our priority queue. Okay, and it's going to be again initialized to heap queue.heap pop because this is actually a priority here, priority queue or a data structure min heap, and we're popping off from the PQ priority queue data structure, right? We're simply extracting the city with the smallest distance from our queue, right? And that makes sure that we always process the closest city first in our priority queue. So while this is true and while we have actually popped out the current distance and the city and stored it in those corresponding variables, we first have to check if the current distance, well, what if that's greater than the distances at that actual city? Yeah, okay, that looks to be spelled correctly, I'll see. And if that's the case, we simply have to continue. Not pass, we simply have to continue, right? And this basically says that if the current distance is essentially outdated, right, it's not the shortest known distance that we can check in distances at that city, we simply have to skip processing it. We simply have to continue on to the next iteration. However, if that's not the case, we have to loop through the neighbor and its corresponding weight in our graph at that city index. So for neighbor, and I'm going to try my best to spell neighbor completely right, so I think that's how you spell it, and weight, again, we're unpacking using 2 iterators for length 2 data structures in the graph. In graph at that index city, at that corresponding city in this iteration, we want to set our new distance, all right, our new distance to be equal to the current distance plus the current weight, okay, the weight at this index. Now, if the new distance that we just initialized, we first have to check, well, is it strictly less than the distances at that neighbor? And I'm actually just going to copy this neighbor here because I don't think that I can actually spell it right, and I think all this should be fine. If that's the case, then we want to set distances at that neighbor and update it to be equal to the new distance. And I just realized I completely butchered the spelling. I'm going to paste it, and like I was talking about, oh, oops. Okay, you know what? Never mind. Okay, just paste that in here. And we want to update it to be equal to the new distance that we just calculated if and only if it's less than the previous value of the distance at that neighbor from that neighbor node. And once we do that, we have to then push onto our priority queue, or heap queue.heap push, or rather our min heap data structure that we initialized to be PQ or priority queue, a tuple of again length 2. And in this case, when we're actually heap queue.heap pushing, we need to pass in 2 parameters. The first parameter is going to be the actual data structure that we're pushing onto, which in this case is going to be PQ. And the second value is the actual, the second parameter is the actual value that we're pushing on to our heap queue data structure. And that's going to be a tuple of length 2, right? It's going to be the new distance, and it's then going to be the neighbor. Okay, I'm having a really hard time spelling neighbor. This should be right. Okay, and again, sorry about that. I didn't really explain this as best that I could. I'm going to reiterate what this actually means. We're basically in this while loop. We're simply exploring the neighbors of the current city, right? And we have to basically calculate the new potential distance to each neighbor, right? And if the new distance, right, if it's smaller than the currently known distance at that neighbor, then we have to update it and push that corresponding neighbor and its value into our queue or into our priority queue. And effectively, once we're done, while we don't have any more nodes to process in our priority queue, we simply have to return distances, well, at n-1, at index n-1. Rather, why? Because this is going to be the shortest distance that we calculated from all the different nodes from city 0 up until city n-1. Right? That's why we're returning the value at the index of our distances at n-1. It's going to tell us the shortest distance from city 0 up until this indexer node from road n-1. Okay, now that we've actually defined our Dijkstra's algorithm helper function, now we have to actually process our queries. So now I'm actually going to initialize my answer. It's going to be initialized to an empty list, and keep in mind it's going to have the same dimensions or the same length as our input array queries. Okay, so now again, this is going to be u unpacking in Python. So for every u and v as our iterators in our queries input array, right, this is what we have to actually base off our computations of. We're going to set graph at u, so graph at that index, graph at that index u, and at that index u in our graph, we want to append the new road, right, which we can get with v. So graph at u dot append v, or rather, this is going to be a tuple of length 2, v, and its corresponding weight 1. Okay, looks like I completely forgot the v. Sorry about that. Okay, so for every u and v in the queries, we're going to append to that row u, that index u rather, we're going to add the new row, right, which is going to be a tuple of length 2, the actual v, and the weight 1. Okay, now that we've actually added the new road, we want to initialize our shortest path, and it's going to be basically a call or an execution of our Dijkstra's algorithm helper function. So shortest path is going to be initialized to Dijkstra. I'm not going to spell that again. I'm simply going to copy it. Okay, awesome. And now that we've actually called it and stored that result in our shortest path, again, calculating the distance from city 0 to city n-1 in our distances, we simply have to basically append to our answer for this corresponding query, answer.append, I think that's how you spell it, right? Okay, answer.append the shortest path. But we can't just say we can append the shortest path. What if the shortest path was never changed to be something besides float of infinity? What if it was never minimized and we never found a new distance that was less than the distances at that neighbor, which is again float of infinity? What if it stayed its original value of the float of infinity? Well, in that case, if it's not equal to float of infinity, we have to return, if it is equal to float of infinity, we have to return or basically append -1 for that query. Okay, so we have to append our shortest path if the shortest path is actually not equal to, and in Python we just use it like this, our float of infinity that we initialize that value or that shortest distance to be. However, if it's not equal to the float of infinity, or in other words, if it is equal to the float of infinity, we have to append -1 for that query, right? We're simply iterating again through the queries, okay? And we simply have to, for each u, add the new road, u comma v, to their graph, right? And we have to recompute our shortest path from node 0 up until road n-1 using our Dijkstra's algorithm call that we defined up here. Okay, and we have to append the new corresponding shortest path result to our answer list. But again, if it never was changed or minimized from the float of infinity, so in other words, if we didn't actually find a path in that Dijkstra's call, we simply have to append a -1 for that query index I. And effectively, we simply have to return the answer result because it would have eventually stored the list of the shortest paths for all of our queries with the same length or dimensions as our input array queries. So unless I made any syntax errors here, this should be accepted and this should be a valid solution. Okay, let's see what I did wrong here. I think I spelled something wrong, but I can't see what I spelled wrong. This should be right. Okay, yeah, there it is. This should be default. Okay, now this should be right. I probably spelled something else wrong as well. Yeah, okay. Okay, there should be a heap. Okay, oops. There should be a P. I don't know why I forgot the P. It should be heap q.heap push. Sorry about that. But now, as you can see, this is a valid solution and it is pretty efficient. So, for a quick high-level rundown of how this algorithm actually works, now that we've seen that it's actually submitted and it is a valid accepted solution on Leetcode, really high-level rundown here. We're basically just dynamically updating our graph once we initialize it as new roads, and they're added via the queries. Okay, and for each query, we have to recalculate the shortest path from CD0 to CDn-1 using our Dijkstra's algorithm, where we store our results in the corresponding indices in our answer array. So for the time complexity of this solution, this is going to be a big O. Okay, I think this is actually pretty advanced. Let me actually just comment this actually. Okay, so basically, I'm going to break this down step by step of how we actually arrive to the final time complexity here, right? It's going to be pretty advanced, and I'll show you guys this after we actually break it down. So, to actually build our initial graph, that's a linear time runtime, right? That's going to be big O of n right there. And for every query, we have to add a row, which is a constant time solution, and we have to also run Dijkstra's algorithm, right? Which is going to be a total time complexity for Dijkstra's algorithm of big O of v plus e times the log of v, right? V is going to be n, and e is going to be the number of rows that we actually have, right? So for the total time complexity, after you actually include the runtime for the initial graph representation building and also Dijkstra's algorithm and adding every row, we're going to have the total runtime complexity. Runtime, I think that's a good way to express it. Complexity. And it's going to be equal to big O of Q times n plus e. And it's going to be multiplied by the log of n. And in fact, I'm going to put that in parentheses so it's a little bit more readable. All right, so to reiterate, Q is going to be the number of queries, and E is going to be the average number of edges per row that we actually add. So Q, the number of queries, times N plus E, and there's our input, and E is the number of edges on average per node, times the log of N, right? And this part is basically just derived from our Dijkstra's algorithm runtime. Right, where again, that's going to be a big O of v plus e times the log of v, right, where v is the number, e is the number of rows, and v is simply our input n. Okay, so quite a handful here. Usually, graph algorithms, especially when you use Dijkstra's algorithm for such kind of advanced problems, is going to have pretty scary time complexities. Nothing too crazy though, you'll get used to it. And for the memory complexity, or the space complexity, I'll just put /memory. Because they're used hand-to-hand, they're pretty interchangeable vocabulary. It's going to be a big O of quite more simple, n plus q, right? And how do we get that? Well, to kind of break it down, we have to actually have or store nodes in our graph, which is going to be a big O of n plus q for our graph storage, right? And our Dijkstra's algorithm for our distances array and our priority queue data structures are also going to be a simplified big O of n memory complexity. And the total is hence going to be big O of n plus q. Okay, so that's going to be it for today's solution. If you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.